In this paper, we present a novel approach of representing a surface as a linear combination of eigenvectors and using this representation to deform the surface. Deforming models is an important task in the animation community. Here, we use the horse model to create multiple deformations using our method and put them together to create the effect of a running horse. Our approach uses the top few eigenvectors of the Laplace operator defined on a surface to create an implicit representation which we call the eigenskeleton. The eigenskeleton is able to capture the salient features of the surface, and using more and more eigenvectors allows us to capture more details. To deform a surface, a user has to first select a region on the surface which we call the region of interest. Based on the size of this region, we choose the number of eigenvectors to use and create the eigenskeleton. Next, the user specifies the type of movement desired and simply starts manipulating this region of interest. The movement can be of translation type or of rotation type. The coarse case is created simply by applying this transformation to the entire region of interest. Once we have the coarse case, we use a simple one-step linear solver described in our paper to convert the non-continuous coarse case into a smoothly deformed eigenskeleton. In fact, steps 1 and 2 are fast enough to let us deform the eigenskeleton in real time. Finally, we exploit the one-to-one correspondence between the vertices of the original mesh and the eigenskeleton to add the details back. Further information on this step can be found in our paper. Here we show how half of a dragon can be interactively rotated using our method. Since adding details takes more time than our linear solver, we usually just deform the eigenskeleton at interactive rates and add the details back when the user is satisfied with the shape of the skeleton. Also, since we do not rely on the user to provide cages or skeletons, it is very quick and easy to deform complex shapes like knots. Finally, we show some more deformations created using our approach. To summarize, we present a simple and fast technique to deform shapes by using eigenvectors. Our method does not rely on the user to provide skeletons or cages, can deform the mesh at interactive rates, and also tries to preserve isometry whenever possible. However, like most deformation methods, we cannot guarantee that the deformations do not self-intersect. We would also like to point out that computing the eigenvectors for very large meshes can be slow.